Okay, we're going to get started. So I'm going to start today by talking about your third programming assignment. It's actually not due for a while. It's after the midterm, but I also wanted to give you a chance to get started on it in case there are any questions, and because this assignment will take you a little bit longer than the last one. And it's going to build on materials from chapters 8, 9, and 10. So by the time you get through the midterm and studying, that week, my guess is you won't be doing a lot of development, so I want to give you a chance to get started on it now. Make sure you're going on. This project is actually very realistic. This is based on some work we're doing for the Air Force Academy, joint with the Air Force Academy for the Air Force and joint with the University of Southern California. This is an extremely simplified version of what we're trying to do, but I thought it would be interesting for you to sort of see something in an interesting setting where you have to deal with a lot of this 3D plane geometry and projection. Come on, mouse. Okay, so our problem is we're dealing with drones that are providing information to soldiers on the battlefield, and so the drone's going to fly over areas and it's going to detect things, and the detection is a big part of what we're trying to do. It's not just to do the display, but we want to detect these people and recognize that there are some people here, some cars here, and there's actually a potential adversary might be hiding around. And so our job is to sort of figure out what they're doing and then display that information to the soldiers in the battlefield. Currently, what the soldiers who are working in this scenarios deal with is they get from their drone a live feed. They basically get to see video that might look like this of what's going on. And for one camera, that's not particularly bad. But if you start getting 4 or 5 cameras, it gets really hard to understand what's going on where. And the bandwidth of 4 or 5 cameras is often more than they can afford to transmit on the battlefield in those kinds of situations. So our task is to give them better situational awareness and to reduce the bandwidth. So as the drone's flying, this particular one here is a DJ Phantom. That's not really what they fly in field, but it's easier for us to work with that up at the academy. So that camera, but all of the drones the military will work with, have a camera on them. And the camera basically has the ability to pan and tilt so it can look around and actually zoom. We're going to ignore zoom for today. That just makes everything a lot more complicated for you. So we're just going to deal with pan and tilt, or in the terminology we'll be using in this class, the camera has a tilt angle, which is how far from, if it's looking straight down, it has a tilt of 0. As it tilts up, it has a tilt that gets larger and larger. That's its tilt angle, and its bearing, which is if this way is due north, as I turn this way or that way, I can know how I'm rotated. Okay, and there's a bunch of sensors on the drone that help it answer all those questions, but it has a north sensing system built into it, and then it can figure out how far it's rotated around. So it does that. Now it has an idea where is the center of projection, which is the optical axis, the view axis. It's got a lot of different names depending on what you read on the internet, but that optical axis is the center of the viewpoint. And that's what that angle is going to tell me. And that angle is not the only angle we have to worry about, but that gives you a feeling. So you'll see when we go through this assignment, you're going to be given, here is the location of the drone, which is we're going to consider that to be the location of the center of the projection of the camera, which is realistically not where it is, but you have to do a lot of work to get from the actual drone's location to the camera location. That's a lot more complicated. It's based on kinematics, but we'll skip all that. So you're going to know where the drone is, and you're going to know what direction it's looking. And from that, you can actually sort of project stuff back onto the ground and figure out where they came from. So we're going to assume this is based on a simple camera model called the pinhole camera, which is actually a pretty good approximation to lots of the things until you start messing with zoom, and then it has some problems. But again, we're going to ignore the zoom. So the pinhole camera, you can actually go and make one of these. Anyone ever make a pinhole camera? For example, watching the solar eclipse last year or whatever? Pinhole camera is a hole in a piece of cardboard, and if you actually do that right, it makes an image of the world. And the world's first imaging system was a tent with a hole in one side and a screen, the tent on the other, and then it made a copy of the world upside down, and you could sort of see what was going on. So the geometry that goes with this is actually very simple. The rays from the world go through the hole as straight lines. Right? And then they fall on this image plane. If the image plane is perpendicular to the hole, where the hole is, you get an image. Now in real camera obscura or real pinhole cameras, the world is upside down. That's really annoying to work with. And by the way, in every one of your eyes, the world is upside down. Our eyes actually see up on the bottom. and down is on the top, but we as humans just learn to ignore that, and we see the world reinverted for us. But to make it easier for the camera, we can actually take what we call the focal length, which is the distance from the pinhole to that plane, and we can make the same distance in front of the camera, and we can pretend that the rays are going through something there as they're on their way to the hole. That just makes it a little bit easier to keep everything upright. But given this, I can now, you can imagine, I could send out through this plane. So if I take the pinhole as a point, and I take some point on this image plane, I can back project it and see where it lands. So if I'm going to compute from this, I have my image, which is upside down. We'll ignore that. We'll pretend we have the front one. And then I can take this, and if I were to go through the bearing and tilt, I know where that ray would hit the ground plane. So if I think of this as a plane equation for the ground and a ray, I can ask where does this ray and this plane intersect, right? That's material you've now hopefully covered. And I can do that not just for the point in the middle, I can actually do it for any point. So I can take a point that's on the edge of the image and I can back project it and say, where will that point hit the ground? And now I will know where that point will be. And with that, you can build a very simple interface where I take all the points, even though my drone was on the side, I can back project each of those targets I saw and put them on a map or on an image overlay, which is cheap to transmit. We transmit the image once, the ground plane map, and then I can put the dots around. And then as the dots move, all I have to do is move the dots. So this is by far the simplest interface, and this will work even if I have one drone on this side of the compound, another drone over here, another drone looking in the middle. It doesn't matter how many drones I have, I can now have pretty good situational awareness. These are just dots, right? And red dots and blue dots keep track of which side we think they're on. So that's pretty straightforward. That's actually not what you're going to do. That's actually pretty well-known technology, but you'll be doing something related to that. It's a little bit more complicated. So what they've asked us to do, in addition to tracking and doing all this other stuff, is we're going to basically take the same kind of information, but instead of just sending down a point, if I think of having found, let's go to it this way, I'll explain images first and I'll go back to the text, right? Imagine that I actually have a little image chip from the drone that says, here's what I'm seeing for each of those 4 or 5 targets. Now instead of putting a little blue dot, I'm going to put an image with the blue. And instead of a red dot, we're going to put an image of what we think is the red guy. And that's important because with just a dot, I can't really tell. Do they have weapons? What are they doing, right? Am I sure it's really a red or a blue dot? What do I do if I'm not sure what's going on? If I actually give the soldiers information, like here's an image of the person, I can see what they're doing. So if they're loading a weapon, I can see a weapon. I can see what they're doing. If they're sitting there drinking coffee, I can see that too, as opposed to just there's a dot and I don't know what they're doing. So the goal is to give them more information, but at a very cheap price. We're not going to send live video. We're going to send little image chips. And we'll only send as many image chips as we can afford to send. So that's the realistic problem. You guys don't have to worry about any of the sending or whatever. But this task is, how do I figure out where to draw that chip? Okay? So this first one, you're going to basically take the central view that we talked about, right, which you can project for anything. If I now think of the image chip as 4 points, it's like square, right, out of the image, I now have 4 points. I'm just going to back project each of those 4, have them hit the ground, and now I get a quadrilateral. It's not a square anymore because it'll be distorted on the ground. It'll be some parallel pipette or quadrilateral on the ground, and I'm going to get the 4 corners of that, and that's what I'm going to compute for this piece. And if we're doing this for the way I showed the image, we'd actually then like texture map this image into this quadrilateral, which we're actually breaking 2 triangles to draw a little bit. And then with that, we can figure out, we can show them what we want to do. So in this case, we're going to assume that the altitude of the area of interest is constant. It's actually not. That makes the problem a whole lot more interesting when there's hills. I have to back project and I have to hit the hills, but that's beyond this class. We'll just do linear algebra. The world is a flat plane at an altitude of 2134 meters, which is about what it is at the target location we're drawing. And then you're going to give us 4 coordinates: lower left, lower right, upper right, upper left. Right. So we're going to go around the quadrilateral in counterclockwise order, right, from the bottom left. And then you're also going to estimate the total area of the target, just to work your math a little bit more. So for testing, you'll be given multiple files that have, here is where the camera is, here's the bearing and tilt, and then the lower left and upper right of the region of interest in the image, which gives you the 2 corners. You can get all 4 of them from that. And then you're going to output the 4 corners on the ground plane and the target area. Again, for realistic things, we would do something more complicated. For computing area, you just have to use a certain number of meters per degree of latitude and a certain number of meters per degree of longitude, which for even a 1 kilometer square area is a perfectly good approximation for what's going on. So you can assume that number would change if I changed around the Earth, right? Degrees of latitude, as you go higher, they become shorter and shorter. So 1 degree as you move around in longitude keeps changing what its distance is. When you get to the pole, 1 degree is a very small distance. To the equator, it's more. But you don't have to worry too much about that for this, what we're going to do here. Any questions on that first part? Ryan?
Is the tilt and bearing in degrees or
Good question. It'll be in degrees. So I don't know what it comes out of the sensor, but we'll convert it to, to degrees. My guess is we actually have a choice, because lots of these things, you have choices. Most GPSs, you can say, give me altitude in meters or feet, but we're doing meters there. We'll do degrees for sure. Any other questions? Here, Mike. Right, so the camera point is this point. It's the pinhole. Right? Then you're going to project it through the image plane. So at a distance called the focal length, right, which is a number you'll be given, which is affected by what the zoom is, you'll be given a focal length and this point, which means I can say how far away this plane is. And then from geometry, I can say I'm this far away, I'm at x, y, I can compute those angles. So you'll have enough information to compute what is the equation of that ray, so you can then intersect it with the ground plane. So in the simple description I've given you here, it's actually missing just a little bit of information. I have to tell you how big is the image chip and a few other things, but all that'll be in the assignment when I post it online. Does that make sense? So, well, the chip, think of the chip in this drawing as the chip is sitting in front of the pinhole, right? And then a ray, so if I choose the tip of the flame, right, that's a point up here, then I can make a ray that goes from the pinhole, hits the image where the tip of the flame is, and then goes out and hits where it is in the real world, right? So if this was the head of a person, that would be going out and hitting the head of the person. Now this drawing is sideways. We're going to be doing it looking down generally, right? So when we see somebody, the ray that hits the top of the head and the ray that hits the foot, right? The ray that hits the foot is on the ground. The ray that is at the top of the head is actually well above the ground, but if I keep going, there's a point where I can project it onto the ground. That's what's going to drive the back end of the rectangle, or the quadrilateral is, as I project backwards, right? This corner, right, went and kept going past the person and hits the ground. Right? In fact, the corners are actually all on the ground. They're not on the person, so that, or at least hopefully. So, and then with that, we should actually be able to then, again, for our project, we'll actually be having dynamic rectangles. Every frame of video, we'll compute new rectangles and decide, do we need to send an update, or is it pretty much the same as it was, and do some things like that. Any questions? Up to 2, right? 1 or 2, it's up to you. Same as we had the last one. Okay, so that's the first part. The third part, we actually, the TA says my description of it online is not really good. I changed it, but I haven't got any feedback from him. So until he and I meet today. So this may change a little bit, but I'll just explain part 2 to give you a general idea. It may change in some small details. And I'll describe it in images first, and then we'll go back to what the text is supposed to do. So the problem with putting them on the ground is I really have no idea where the drone is, what direction the person is facing, and what the information is, right? It's just an image on the flat ground, and that can be very hard to interpret. So what we really want to have is the object as a 3D object in the scene, so we can sort of see what's going on. So a simplified version, we're building more complicated structures, but the simplified one here is we're going to have a plane that is perpendicular to the view angle. So if I'm looking at from down the viewing axis, right, this plane would be perpendicular to it. So if I'm straight overhead, then the plane would be parallel to the ground. But if the person's on one side of the building, then their plane would be facing, in this view here, if the camera's over here, right? So I'm looking at it this way. So I have an idea now relative to what I see on the map. Where is the person looking and what's going on? Because that plane is facing the same direction as the camera. The problem with a very thin plane is you can only see it from some angles and not others. So we're gonna augment it by having a plane that goes from the top of that and projects back down to the ground. This has a secondary advantage that for a person it's not a big deal, but if I have a car or a truck or something and the drone is on one side looking at it, it obscures what's behind it. The drone can't see anything in its view cone. This area behind it is called the view cone because the occluded cone, sorry, because nothing in that cone can be seen. The camera can't see it because the object's blocking it. So there'll be a second plane which is really connected to this one at the top and is parallel to the viewing angle. This also lets, if you look at this in a 3D display, you know exactly where the drone is. The drone is not just on this side of the person, but it's actually over here. Well, you can't see the mouse, but it would be someplace on this side, but up a little higher, and make that work out. Now, one of the things my TA noted is that this drawing is not actually correct. This is actually a drawing from when we were trying to make the person vertical and the back plane parallel, and we're still not exactly sure what the soldiers will want, so we've been experimenting with different ideas, but that's why I will update this online so that you get the basic idea. But one of them will be perpendicular to the view, the other will be sort of parallel to the view. And then, again, you guys aren't doing any of the graphics, so you don't have to worry too much about it. So this can be done solo or a team. You can use any languages from Java, C#, C++, Python, JavaScript, C. If you have something else you really want to try, let me know. We can talk about it. As before, you're going to have your code in GitHub. So one thing I didn't mention. So we're going to give you some test files, but in a real problem in the real world, your boss really rarely gives you, here's the test file so you can make sure you're doing it right. You have to design them yourself. So in this assignment, you get to design, here are 3 example files for your own testing. I will give you the specification of what that file will look like, but it really is just, so in this case, it's actually on here, right? You're going to be given 10 numbers. Actually, I think it's now 12, but the camera point, which is 3 numbers, the bearing, the tilt, the lower left and upper right of the region of interest, the camera focal length, and the camera chip area will actually be a constant, so that's not actually given to you in the file. That's why I forgot about it here. And so those are the 10 numbers in those orders. You can assume they're all going to be floats because they all will be floats. And then using that information, you can do the geometry and the linear algebra to find those intersection points. Any questions? So I'm not, in this assignment, making you turn in design documentation a week early. I do, however, heartily recommend that process so that you can make sure you know what you're doing. You can start thinking about the design. Don't worry about coding it yet. Just think through, what is this problem? How do I represent these things? What are my data structures for the planes and the lines? And then how am I going to actually solve the math, right? And once you're confident about that, then the rest of the coding will go much easier as opposed to trying to code it up and sort of see how it goes and hope that works out. So think through the math first. Okay, let's go ahead and turn on our clicker. Okay, how engaging was the description of programming 3? Okay, last call on that. Not as engaging as I thought. I'm not sure why. I don't have any questions for one. And you don't have to answer this, but since like 9 or 10 people thought that wasn't very engaging, is it that I went too fast? Is it stuff like that, or why was the description of the program assignment? I expected that would be an engaging thing to hear what your assignment's going to be. No one wants to answer? Hannah? Okay, so try to. So it is not a trivial problem. It's very realistic. So you might be like, I'm lost. I don't know exactly what to do. So hopefully you can go back and work through that and come visit my office hours if you can. But okay. So if you think about it during break, you can also come back up and you can ask more questions. Okay, so now, so from the journals, I saw that a number of people struggled with handedness, and I do all the time, but I have some ways to go through it, so I was going to go through some of this to make sure everyone understands handedness, coordinate systems, and how that affects rotations and whatever. And as you've seen in class, I get this wrong all the time, in part because depending on what library you work with, sometimes they're right-handed coordinate systems, sometimes they're left. It's a function of convenience for what they're trying to do. And then, see, I have this other problem as a dyslexic, right? This is my left and this is my other left, right? I get them confused. But so for the right-handed rule, right, this is one I struggled with actually in high school, right? Which is, they say, you know, well, these describe a coordinate system, but so do these, right? And when I line them up, right, I can, right, try and make them line up in the right way. So which way, what's the process of doing it? So for right-handed coordinate in physics, you know, you talk about curl and divergence, whatever, but your right thumb points along the axis of rotation. So if I'm trying to set this up for rotation, in a right-handed coordinate system, I take my index finger and I go to the lowest index that I'm not rotating around. Then I put my middle finger on the second one and my thumb points in the axis of rotation if it's right-handed, or my thumb will point the axis if it's left-handed, right? So go through them in order. If it's X, Y, Z, and I want to rotate around Z, then I do X, Y, and then that gives me my Z. If I'm going to do rotate around Z, around X, then as in this drawing, I actually do Y, Z, and rotate around X, right? So you go from lowest dimension, skipping if you want to rotate around one, right? Index, middle, and then your thumb, right? Because otherwise I can say, well, I'm going to do, you know, index. So if I want to do, if I do them in the wrong order, then I can make it look like it's right-handed because I did. So let's do rotation around Y. So this is the one that actually led to the questions some students have. So if I take my traditional coordinate system, I try and rotate around Y. If I do Z, X, Y, I can make it seem like it's right-handed because I actually did them in the order Z, X, Y, right? Which actually then corresponds with that drawing, Z, X, Y. The problem is that's not enumerating them in the right order, right? I have to do them in the order X, Z, Y, and then for the natural way of looking at the, so yeah, if I do X, Y, Z, I get my rotation that way. But if I do X, Z, Y, I have to use my left hand to make them line up with the coordinate system that we're actually using. We're using a right-handed coordinate system. So when I do X, if I'm trying to match this coordinate system, which is our right-handed one, right? If I do X and then Z, making them point in the same direction as Z, then to make it Y work, I have to go up with my left hand, not up with my right hand. If I did X, Z, Y would go down, right? If it was right-handed. So naturally, the XZ plane is considered to be left-handed, which is why when I go to do rotations, it's a counterclockwise rotation in its left-handed coordinate system. But when I look at the rotation matrix in 3D, the minus sign is on the bottom for E2 instead of up here, right? And that's why that happens, because naturally it's actually a left-handed coordinate system if I want to go counterclockwise, or if I make it right-handed, then I just have to go clockwise, right, instead of counterclockwise. So that gives you a rotation, hopefully an understanding why the rotation for the y-axis, or the E2 axis, seems to be backwards compared to the others. Now, some other people said they really struggle to remember which one's which. So if you can go through all the handedness, you can always remember it from a handedness point of view. But handedness is tricky, so I actually find it easier if I want to remember this. This is the way I learned it. If I want to do the coordinate system, I actually, a little bit like I play when I'm doing determinants, right? Take the rotation matrix, which I know for x, right, which is this one here, right? Ones for the x's and then the cosine minus sine that you normally see. make 4 copies of it, sort of append it to itself, and then I can just read off in the order x, z, y, and it's easy to tell which one's x, z, y. So I'm going to take this rectangle, that's my first one. I move it over 1. Now I get the z dimensions rotation matrix, and I can tell it's a z because there's the identity 0s and 1s in the z column, and then I move it over 1 more time, and I get y. And if I do it this way, the sign will always show up in the right place because I can never always remember which one should be which. So that gives you another way of trying to remember how to get the right rotation matrix for the different axes. Any questions on that? Okay. So since 3 or 4 people had that, I wanted to cover before we get into our clicker questions. Okay, so consider the vector v100 and w111. Compute the area of the parallelogram formed by the vectors v and w. This is the area, not the volume, of the parallelogram. And you can work with a neighbor. If people are struggling, so I did a little bit of drawing here. My art's not that good, but in 3D we have the point 100, which is on the x-axis. And then we have the point 111, which is like outside the sort of intersection 111 value for all. Right? Those are two vectors. And when I connect those vectors, right, they form locally a plane, and in that plane is a parallelogram, right, that I'm asking about its area. Okay, we've gotten rid of a couple of the obviously wrong answers. Okay, I'll give you another 30 seconds. Okay, last call. Okay, so Brianna, Tom, how did you solve this? Right, okay, so you take the cross product and then you take the magnitude of the vector that comes out of it and that gives you the area, right? That's the easy way to solve this one. So take the cross product, you get the magnitude of the area, so, and I'll go through the cross products in just a second, right? And you get the answer is the square root of 2, so the answer was C, right? So to do the cross product again, there's lots of ways. Different people had their own, but I go through the one I always fall back on because I can't remember the others, right? So if I take I, J, K, the three axes, or X, Y, Z, as I wrote it up here, right? You do the cross product. You're just going to take. We're going to do that again. X, Y, Z, 1, 0, 0, 1, 1, 1. So this like copy and replicate is done. Then I take this value minus this value, and then notice they both go through the X, right? So those are both 0. Then I do this value minus this value. They're also 0. And then I do this value, which is Z minus. I have a. Oh, so one is wrong. My mind's too off. Z 1 1 1 Y minus 1. So that gives me my vector of 0x minus 1y and 1z, which is what we have up there. One thing about this is you have to be able to draw straight. But, so that gives you how to go ahead and do it. Now, I also wanted to point out something I learned last year. We had students doing stuff in C#. There's some name confusion that you might have to deal with if you're working in Windows.net. In Windows.net, there's a function called cross product, which will take 2D vectors and do something that is completely unrelated to the 3D cross product. Right? So if you're coding and you're playing with cross products and you give it a vector, it will return something that's, I don't know, they call it cross. It's the x of one times the y of the other minus the y of one times the x of the other, as opposed to the 3D cross product. So that's just a little word of warning. If you accidentally declare a 2D vector and call a function called cross product, you will get an answer. And it will be a scalar, and it won't be the right thing. Whenever you do cross products of vectors, the answer is always a vector, right? So, but we had some students last semester who did that in their programming assignment, and then they got very confused because it's like, but it keeps giving me a scalar. And I didn't understand it for a while until I looked through the Windows documentation. I said, wow, that's convenient. Okay. Simple, do this one on your own. What is the norm of P minus Q? Another word for norm is magnitude. Oops. Oh, my battery died. Okay, now there's a new one. Okay, this is pretty easy. You should be done this by now. We'll give you another 15 seconds. Okay, last call. Okay, so we got Henry Bennett. How did you solve this one? You do it with the cross products. No. Because I don't know how to get the norm from a cross product. Stephanie? Can you speak a little louder? Right, that is the norm. So you subtract them, you get this, and then I do the square root of -1 squared plus -1 squared plus 0 squared, and I get the square root of 2, and the answer was C. So that gives us the magnitude, or the norm. So now, same vectors. Form an equation of the line that bisects the points P and Q. Okay, think of this as if someone's shooting at you from P and you're standing at Q and you want to put a shield of energy halfway between them, what's the equation of the shield? And you can work with a neighbor on this one. I've already figured out your answer. You might think of how might you check your answer given the description of the problem. We still have a bunch of people going, so I'm not going to call it yet. I'll give people another 45 seconds. We'll go to 6 minutes, puts me. Okay, last call. Okay, so I'm trying to give people points by calling it people who need points. So that's don't worry if I'm calling you. It's because you haven't gotten many points so far throughout the semester in terms of class participation. So let's go for Elijah Lopez. What was the midpoint of P and Q? No. Austin Payne. Austin, you back there? You're not sure. What's the midpoint? Actually, well, okay, Chris. Jonathan, okay. You keep moving around. Okay, Jonathan. So, first we subtract, add them and divide by 2, so we get 1/2, 1/2, 1 as our midpoint. So now, what's special about the midpoint, Jonathan? Right. The plane has to go through the midpoint, right? Okay. Okay. Well, so I want to give somebody else some points for the next piece. So you got that it's on. Why don't you just go to your left and and what's your name? Yeah. Zach, okay. Zach, yep, okay. Jonathan, Zach, go ahead, Zach. So now that I have the midpoint, what's the next step? Vector, so what vector do I get? So how do I get that vector? Okay. Can you speak up? Right, so I subtract P and Q, or actually I could subtract midpoint, but I'm going to do P and Q. So we got M. Now the normal vector for the plane that's going to bisect them has to go from P minus Q, or Q minus P, order doesn't matter, and then I divide by the norm of that to get me a unit normal, right? I could actually have used the regular normal, but then the equation for the point normal form of a plane requires that the point normal be in unit normal. So I compute n, q minus p divided by the norm, which we had just computed, gives us 1 over the square root of 2, 1 over the square root of 2, 0. Right? And now the point normal form, I do n dot x minus m equals 0. I do, here I have n dot x minus m, so I put the x's in as little actual literal letters, right? And I get the equation that comes out of that, which is 1 over the square root of 2x1 plus 1 over the square root of 2x2 minus 1 over the square root of 2. So the correct answer was D. Now, a lot of people got the answer A. Okay, so to get the answer A, what did you do to get the answer A? Because here's how we went through everything else. What did you do for A? Right?
We have a vector, subtract the and then plug in the numbers from that vector.
Right. Yeah, so in the point normal plane equation, the standard letters used are n dot x minus p. Unfortunately, we used p to be one of the 2 points, not m. So if you put in p, whoops, if you put p in this equation, you get wrong things, right? So it's not this value of p, so that led you down the path of A. And if you, so to get like some of the other answers, B, if you take, so what was B? If I just took m and I put those as coefficients, then I could get like B. Okay. Now, I also suggested that if you solve this, so did anyone actually check their answer? We did have a few people move from A to D after they checked their answer, I hope. But anyone check your answer? How did you check it? How might you check the answer? So we have the equation that we think the answer is. What could I do to check that that's actually... So what do I know if the plane is bisecting those 2 points? Okay. The plane should be equidistant. Hannah? So if I put P and Q back in, what I will get, if I put P and Q into this formula, I actually get a value that allows me to say how far are P and Q from the plane. And since it's supposed to be bisecting, they should be equidistant from the plane, then that actually works. I put in P, I put in Q, and I get like 1 over the square root of 2 for the distance for the plane. Okay, this is one you should be able to do on your own. We'll do it quickly, a 30-second question. Knowing that U and V are linearly dependent, what would you have to do in order to see if U, some third vector, is contained in the same subspace spanned by V and W? Sure. No. Q minus P and P minus Q wouldn't change, right? So it'll change what side of the plane you put your equation on, and then a bunch of signs like multiply themselves back out and you get the same equation. Anna. Yeah, it's a big font. Yes, it helps to be able to read that last word. Say again. Q. U is a point. Well, U is a vector. V and W are vectors, and we're trying to ask: is V in the subspace spanned by U? Is U in the subspace spanned by V and W? All 3 are vectors. Are A and C. A and E. Looks that way. Probably a typo, but... Okay, this was supposed to be quick. I'll give you another 20 seconds. Okay, last call. Okay, most people did get this one. The correct answer was D. Calculate the volume of the parallel pipette formed by U, V, and W and check if the volume is 0. Right, this is really just so a subspace spanned by V and W, so V and W form a plane, and if the parallel pipette has, if U is in that plane, then the volume will be 0 because they're all in the same plane, right? Which is really why the answer is D, so you compute the volume through that. Okay, so that we just talked about volume. So how does one compute the volume of U, V, and the parallel pipette formed by U, V, and W? You should be able to do this on your own without chatting with your neighbor, but people are already chatting, so go ahead and chat. Make it fair for everyone. Okay, last call. Okay, and so most people did get this slightly trick question. The answer was E, all of the above, right? I try to make it obvious by giving you D triple scalar product, which is the name of all of A, B, and C, right? Triple scalar product is one vector dotted with a cross product of the other two, right? The cross product gives us the area, and then dotting it with the other vector actually makes it into a volume because it gives us the times the area in the other direction kind of thing. And so B and C are just what are called cyclic permutations. If you notice, U, V, W, V, W, U, W, U, V, they're always in the same order. And any of those cyclic permutations always produce the same answer because it's really just a relabeling of things. But not all relabelings produce exactly the same answer. If I had done U dot W cross V, I'd have gotten a negative change because I actually flip things when I change the order an odd number of times. Cyclic permutations are okay. Okay, how engaged were you in the last 5 minutes? Okay, last call. Okay, for those who answered D or E, why were you not engaged? For if you answered anything else, please answer E. I'm finding it hard to interpret these when like only a few people said they were even slightly disengaged, and then lots of people answer why. Makes it hard to understand what's going on. But okay, did I start that one? No. Okay. Okay, last call. Okay. So above our two properties, what cross product properties is represented by the two figures above? Do this on your own. Okay, give me another 20 seconds. Okay, so Zach Fish, what is this property called? You went with B, antisymmetric. No. So it's non-associative is the name of the property. The correct answer was E. So these are a bunch of the important properties of the cross product. This is probably the first operator you've experienced in your math career that doesn't actually associate. Most things associate, like the order of parentheses doesn't have a huge impact, but for a cross product, it does. Right? So U cross V cross W is different than U cross V crossed with W. Right? They're actually pointing in different directions. But it is homogeneous, it is antisymmetric. Antisymmetric being V cross W is the same as minus W cross V. It does distribute, but it doesn't associate. The right-hand rule, orthogonality. So, okay, simpler question. Let's consider the dot product of S and T. Do this one on your own, shouldn't need. Okay, I'll give you another 25 seconds. Okay, last call. Okay, Galen, what'd you get for this? 4. That is the correct answer. In fact, most of the other answers aren't even the right dimensions, okay? Dot products produce numbers. Think of it as a little dot. After whatever you take dot products of big vectors, they become a single number. It's a little dot after it's done. Cross products and matrix products produce bigger things. So only A and E were in the running. And if you do the math, it's really just the product of -2 times -1 plus -2 times -3 plus 2 times -2, which add up to 4. Okay, the second most answer was D, which is the cross product. Interesting question, but not the one I asked. I'm not sure how you got, oh, so C, a bunch of you got C as well. C was the pairwise product. That's actually called a Hadamard product. It actually exists in linear algebra, but is rarely used for the kinds of things we do. Okay, consider the vectors P and Q, which you've already seen today. What is the sine of the angle between P and Q? You should be able to do this one on your own. Okay, we'll give you another 30 seconds. Last call. Okay, so class was pre-split on this one, so let's hear from Chris, Alex. How did you solve it? You didn't solve it. Angelo? You guessed. Okay, not good. Back, middle, yeah. Right. So using using the identity that the norm of the cross product is equal to the norm of the two vectors times sine of theta, right? You just compute the cross product, take its norm, which gives you square root of 2. Right? We've already played with these vectors a lot today, so the cross product was 0, -1, 1. And then that gives the norm of that is square root of 2. And the bottom we have the square root of v, which is 1, the square root of w, which is square root of 3, and that gives us about 0.82. So that puts it together. Did anyone else solve it a different way? No, not Joseph, no. Chris. Okay, that's not even a way I thought of. So you found the cosine by how? Doing the dot product normalized, right? So that's one way. Here's another way, which is to remember that sine squared plus cosine squared equals 1. So you can compute the cosine and get there that way. But once you know the cosine, you can get the angle. From the angle, you can use your calculator and get sine and whatever. So, but the real test here was to check that you understood the identity of sine's relationship with the other two. Okay, given U, V, and W, compute the volume for the parallel pipette defined by V, W, and U. You can work with a partner. That's fine. It is for a right triangle. No. Well, I guess when you say that, there's a lot of things up there. What? So if you use the vector u cross w, u, right, you actually see the draw. So it is a right triangle. So you're getting cosine of the angle. What you do is cosine. I'm not sure why you're using the cosine there. Go over that in a second. So I'm not sure what your thinking process is. We'll give you another 30 seconds. So Brian. Okay, give you another 15 seconds. Last call. Okay, so most people got this. The correct answer was B, right? Which you get by doing the triple scalar product. V dot W cross U, or if you want, U dot V cross W, right? You have to do them in the right order, but any cyclic permutation is already okay. We talked about that, right? So if I do W cross U, let me go back, make sure I do that before. It was W 1 1 1 cross U 0 0 1 I J K 1 0 1 1, and then I get 1 minus 0 I plus 0 and 0j plus 1. Okay. So I get 1 0 1. Now I'm going to dot that with 1 0 0, and I get 1 0 1 plus 0 equals 1, which was B. Okay, very quick question. This one you should be able to do your own. When are two 3D lines skewed? Jeremy. Yes, you have to do them in the, right, so, well, yes and no. You could get -1 if you did them in like, if I did U dot W cross V, I would get -1. That was the correct answer, was 1. Right. So I did it different. I did it in the order they were actually stated, which was U, V, W. Right? But so as long as you do any cyclic permutation, it'll be the same. If I do an acyclic permutation, so I just swap 2 items, then the sign changes to by -1. Yeah, it's true. If you figure from a volume, you can do whatever order you want and then take the absolute, right? But actually, negative volumes will be used. It actually has an interpretation, which is the volume has been inverted because we flipped it's like a reflection plus volumes. When we do determinants and you use determinants for volumes, you'll also get negative numbers, which means the volume was preserved, but the sign changed by left-handed to right-handed. So, last call on this, by the way. We should be about done. Okay, so the correct answer was B, if the lines do not intersect and are not parallel. In 2D, lines either were parallel or they intersected. In 3D, they can be like this, right? They're not parallel and they don't intersect. They just, there's still a point where they get nearest each other and some other things, but they don't necessarily touch. How engaged were you in the last 5 minutes? Okay, we'll go ahead and take our break if you want to answer this one, but go ahead and take a break. Be back by 9:30, so you get about 5 minutes.
So I have a question about the linear domination. So in the final build, do you want us to cycle through all the input files?
Yeah, so yeah, well, there's 3, right? I gave out 3, I think.
There's 2 on canvas, but I'll check again.
So I'm sure I put up a third one.
Okay.
Yeah, there's
Okay.
3. Yeah, cool.
So when the first one, when player whatever wins the first one, then we move on to the second.
Well, so you can just, you can just run it 3 times. Right? It's not like you have to have a program cycle through.
Oh, okay.
So for turning all of our stuff in, should it just be the source code input files, executables, and documentation, or should we also include like our Visual Studio solution and program and all that, or should it just
Since we already have access to the repo, it's enough for you to turn in the code, your description of who did what. If you work by yourself, that's easy. But, and then the inputs and outputs will actually go to the repo where their solution should exist if we need it.
So what do you actually submitted to Canvas?
Your code, the inputs, outputs, and description of who did what in the grades.
You want the outputs? I thought in the description it said just have its console outputs.
No, reads and writes files.
Okay.
So you can redirect your console output to a file. I don't care. That's how you can get that. But yeah,
Okay.
it makes it much easier for Tia to grade if he can read it. He'll only dig into the code if it doesn't do what it's expected to do.
Okay. I'll rewrite that.
So, okay.
I've been getting my Booker
Points. Yeah. Well, so you sent me the number last week. Yeah, I just didn't get to. I was traveling last week, so I'll fix it today. So the number's in there. There's a couple of people who have numbers and that's not associated with their name, so I'll get that fixed.
Okay, so then for this program, as you admit, I know, correct?
Yeah.
So then,
11:15.
so for the GitHub, how do you have the files? We have the input files that you gave us.
Mhm.
We have create 2 of our own, correct?
Yes.
So when we have those, where we put those in GitHub, we just like
Put them in a directory, right? So your GitHub should be like a copy of your directory. So everything that's in your directory will be then.
Okay, because I watched the video that you linked and it's like showing how to GitHub. For some reason, my computer's stupid and it won't like do exactly what your computer does.
Okay.
It's like, so like sometimes my code works, then I like turn in, I was like, the grade is like, none of this code's working. I'm like, what? So it's kind of weird. So,
Well, no, so that can be because like he has different libraries. That's why we want you to have all the stuff in that directory. You
Yes,
can rebuild it. So.
that's why I'm gonna put some pseudocode. Some of my code doesn't work sometimes, which is weird.
Okay, that is weird. So you might actually stop. Well, you can't stop writing one for some reason.
Yeah, because my schedule's all over the place with like work and classes and like folders.
So yeah, you can have. So I would go for the code and explain this. But if your code works, right, pseudocode to explain it, right. If it's got a bug in it, don't write pseudocode to explain it. And
Just
try and find
fix
the
bugs.
problem.
Yes, sir, that's what
Or at least the code is pseudocode as well. Right?
Yes, sir.
Okay.
Just want to make sure I get this right. So for the normal version of Player, it takes user input and stuff like that. Do we still take the user input for board size? Or is that a fixed board system?
So having user input was an option. It wasn't required.
Right.
So you have to have somebody know size, board sizes, and the number of terms to skip. So.
Okay, makes sense.
So I forgot to sync my iClicker with fake out, like I did like 2 weeks ago. But then Blackboard or Canvas X now didn't input like the
The
first
first 2 or 3.
2 or 3, yeah.
So I have to do it for physical clicker. I will have to go back and see. So send me an email so I don't forget.
Cool.
There's got to be somewhere. So I have like everyone's answers from everything. So I've always figured it out. It's just I got to know how to figure it out.
Yeah, I know. I knew it wasn't like difficult, but I was like, yeah, I should probably tell him.
Yep, you should. Those are both parallel, but so is 2x, 2y. Any multiple.
So if you have, say, this and this in front of the vectors of each of these, is it going to be the same?
If you normalize them, so the unit vector is even this one. If you normalize it, oh no, no, sorry. So it would be the opposite. Ignore the sign.
But if you take this and normalize it, it's going to be the opposite of this.
But it'll still be opposite. So
So
that's the question.
it'll still be parallel.
Well, so that's the question: is it parallel or anti-parallel? Anti-parallel. Because sometimes when this versus this matters, but not really.
So I had a glitch with the testing. Used this method, but it always returned the correct answer.
Well, so it's possible that in the game you can't actually get to the end scale. No, you could. If I have my board and I did this versus this, these are still parallel. But delta x, delta y are not the same. So it depends on what x and y are representing. If you get them as a difference between these 2 points, then this would be 1, 0, and this would be 4, 0. Okay, we're going to get started again. So I got a couple questions during break about the programming assignment due today. So just to make sure everyone knows, what we're looking for you to turn in on Canvas is your code, your inputs, your outputs, and if you're a team, who did what and how you want the grade split, which is part of why we do stuff in Canvas. And in there, you should also cite your Git repo, although we should know where they all are by now. You don't have to turn in compiled code. You don't have to, we just want the core code inputs and outputs so that it's easier for the TA to grade. He will go to the repo if he needs to or if he wants to, right? Depending on if he sees something he's not sure what's going on, he may go look at the repo. Don't zip up all of your solutions and everything else. That's what the Git repo is for, so we don't have to deal with all that stuff. Your own inputs and outputs were expected to be there as well, so there'll be the 3. I've now posted another one over the weekend. So there's 3 from me and then yours as well. So then have as text files the inputs and the outputs. Any other questions about the assignment to turn in today?
For the output, does it have to have the list of content saved or did you move it?
Well, as I went through in class, I would expect to see every move showing the lines as they're drawn, right? So it's because if you're playing it, you want to sort of see that as you're playing. So. Any other questions? So I would like to see, when you turn it in, right, your file will say, here's the board after the first move, here's the board after the second move, here's the board after the third move, right? So it makes it much easier for us to understand that you're doing the right things. Ryan?
Should the play wherein the 2 modes of the game is the one you create, where you think of all the inputs and you input them to the text file, and there's another where you inputs, where you get your inputs during the game. Do you want a text file for the easy mode or just the advanced mode?
Just for the text file mode, right? So we don't need, so the interactive play was just easier for you to do your design and testing, right? If you're doing I/O and you've done streams properly, it's really just running it with a different command line option to get one or the other, so it doesn't actually change anything in the code, and that's fine. So you can redirect inputs and outputs on your command line when you run it. If you're running from a console, right, you can save it to a file and do it that way. That's okay. But it should all be one file, not like a file for every move. It should be like, here's the game, series of boards together. If that's too hard, that's not a huge deal. So just explain what you did carefully then. Jeremy? So in Canvas, each of you will turn it in, right? Because each of you have to have your own way of saying, I did this, my partner did this, here's how I want the grade split. If you have to turn that in together, then you can't be as honest as you might because you have to show your partner what you're saying, right? And if you and your partner have not worked out well and you want to say, I should get 70%, they should get 30%, they really didn't do their job, and we're not partnering together in the future, that just makes things awkward. So we go for personal statements that way separately. It also makes it a little bit easier on the TA. He gets one. If he's already graded it, then he'll be able to say, oh, I've already graded this, I know what the score is, and I know who this is associated with, instead of trying to figure out carefully where each person is. You can't forget one this way. Okay. Okay, then back to Chapter 8. A lot to go through. Just a comment, some people ask in their journals, right? So this week we did 8 and 9, but next week we're doing 9 and 10. And given the program was due today, we did not actually have a quiz on Chapter 9 because I knew people would be scrambling to keep up. And so I just pushed quiz 9. Next week you'll have quizzes for 9 and 10. Even if you did all the reading and watched the videos, that's good. You'll get to it. We might get some clicker questions for 9 today, but it's not like we're skipping Chapter 9's quiz. We just pushed it off till next week. And then another question that came up both in journals and last week, I will be posting sometime this week a practice midterm exam, right? So you have some time to look at it and whatever. We're not going to have a whole class review, but I will have the practice midterm out so that if next week you have any questions, you can ask some of those questions. We can go over 1 or 2 of them, but I'm not going to go over the entire exam. The exam are very much the questions like we've done. I will tell you the midterm exam will be pretty much the format I'm going to give you. That's pretty classic for me. Part closed book, part open book. The closed book, part closed book, part open notes. In open notes, you're allowed to use your notes, not your textbooks. No online devices. The closed book section is largely vocabulary and some things that you need to be able to do without looking in your notes, like matrix multiplication, whatever. The exam will probably be between 60 and 75% exactly the questions that you see on the practice with different numbers. Right? So that is, the questions will be similar, and I'll have a few because there's still some studying of other materials. But if you go through that exam and you could answer every one of those questions when you change the numbers, you won't fail. Right? You'll get 60% of it because it'll be questions you've already seen. So it's good to practice that. Oh, sorry. Sorry. R2. That's R cross U. Not R raised to the power of U. Sorry. And now I've restarted it. Brittany. So I'll give out the practice exam. So you'll see the format. So closed book will be questions you can't use your books or notes for, right? So you have to just know that kind of stuff. Some of it will be vocab, some of it will be like maybe some multiplication, some very simple like dot product. If you have to look up how to do a dot product every time you do one, you will never finish things, right? So some of this will just be stuff you just look at. Again? Oh, absolutely, yeah. In fact, you don't have to wait. I mean, if you have questions about the practice exam, you can also just send me an email. You don't have to wait for my office hours. But my office hours come with candy. My email does not. Okay, we'll give you another 30 seconds. Last call. Okay, well, most people did get this. As people said, they wanted to practice these. I made sure we had lots of them. You've now pretty much got the dot or the cross product down. Here, actually, instead of doing the design way, I did it the cofactor way. So I just put down the elements, right? But most people are getting that. So if not, practice a few more of them. If you need to practice, you can always just Google cross product calculator. You'll find one where you can put in some numbers and it'll tell you what the answer is, and you can practice until you're very comfortable with that. Consider the plane given by this equation. What is the distance of this plane to the origin? How far away is this plane from the origin? At its closest point. You can chat with your neighbor. Give it another 15 seconds. Right. Again, we're computing the distance of the plane to the origin. Okay, last call. Okay, so most people got this, although many people were tempted by A. The correct answer was B. You insert, assuming that the point normal plane is in using a proper unit normal, then we insert 0 in the equation. We see the distance is 2/3. Actually, if you insert it in, you get a value of minus 2/3. But it's got to be 2/3 to be the distance to the origin, right? So that gives us our distance. It's also important when doing this, you can't just take a plain equation and stick it in. It has to be one that used a unit normal, which means I can look at the coefficients of each of these three, square them and sum them up and check that it's equal to 1. So in this case, just to check that that's true, I could do that. So if I give you an equation and it's not normalized, you have to normalize it first to make sure that it's in point normal form, or unit normal form. Okay, since we just talked about normalizing, let's do a quick normalization. This one you should be able to do on your own. You get 30 seconds. Okay, 30 seconds was clearly too short. We only have half the class. We'll go for a full minute. Okay, last call. Okay, so who can explain how to get the answer B? Right, you added all the digits together, took the square root, but that's not how you actually normalize. You have to normalize by taking the sum of the squares, right? So I get the normalization, the norm of that is 1 squared plus 2 squared plus 3 squared, which is 14, and so I get the norm is 14, and 1 over the items divided by the square root of 14 gives me the answer D. Okay, another clicker question from the journal. We've already done one like this, so you should be able to do this one on your own. Okay, we'll give you another 15 seconds. Okay, last call. Okay, well, so how many people recognize this problem? It was exactly the same question we asked earlier, right? Just with different other alternatives. And still, we got like 10 people who went for the alternatives. Correct answer was A, and this time we changed the letters up, but same thing. You do the cross product. This one actually gave you the formula. You do the cross product divided by the norm of each of them, and you get 0.82. Compute the point normal plane equation given the vector for the normal V and the point P. Sorry. Properly done ones, yes, but you can still get an equation that works. You know. Okay, so we got most of it. We'll give you another 30 seconds. Okay, last call. Okay, so most people did get this. The correct answer was C, right? Which we can get, oops, right, by looking at, if this is our implicit equation, oops, we can just read off from our normal, right, n1, n2, n3, and then d is minus the pairwise product. This is really just taking n dot x minus p and expanding it out. So if you just want to try and memorize stuff, personally, I just always do the dot product. It's easier. Now this form is actually not in normalized form. It would be better to normalize this. This function, if you put in a value of x, it will tell you what side of the plane it's on by the sign of that number, but it won't tell you the actual distance. You only get distance if I had normalized so that I divide by the square root of, what, 3 squared, 4 squared, 1, whatever that number is, 25, right? So that wasn't one of your choices, right? Once I have a plane equation, I can multiply that equation by any constant I want, and it's still true that if I'm on 0, I'm on 0, because multiplying by a constant other than 0 doesn't change it. Okay. Consider the system above. What is the first shear matrix used in Gaussian elimination? And yes, it's only 2 by 2. We're going back a little bit, but there are still people struggling with shears. Jeremy. So I don't, given that I started the question, it must have started it before I had this projected, so you're seeing my manta. But you can still see the question on the screen and still answer, right? Okay, I'll give you another 15 seconds. You got most of the answers in. Okay, last call. Okay, so we got a pretty interesting spread here. So we had 10 people answer E. How do you make E work? So 10 seems a little high for just random guessing. So a process you use to get E? E is not the correct answer, but right, so if I multiply E, I don't get a matrix that is upper triangular. A was tricky. A lot of people answered A. A will actually give you a triangular matrix, just a lower triangular one. The correct answer is C, right? You multiply it out, right? And so you can get there by looking at this matrix and saying you're going to multiply by this number divided by minus that number, and that tells you what to put in there, or you can just sort of walk through it. Right? Guaranteed, your midterm will have some place where you will have to shear. So practice a little bit of shearing. Okay, one more point distance question. What is the distance of the point y to the plane given by that plane equation? You can chat with your neighbor. Give you another 20 seconds. Okay, last call. Okay, so who wants to justify the most common answer? E, none of the above.
I didn't know that a justification is that that's not a normalization form, so
Okay, well, that's not why the answer is not E, but so you didn't simplify. Okay, so yeah, so both of those answers hint at part of it. The correct answer is B, right? You need to put it in point normal form with a normalized vector, right? So if I look at this vector, these three items are not summing up to 1. So I compute the norm of that vector to be the square root of 9 plus 16 plus 25, which is 3 squared plus 4 squared plus 5 squared, which is 5 to the square root of 2. Personally, I would have probably left it as the square root of 50, but hey, this came from a student, so I just went with their approach of doing it, right? So then I compute the revised equation, which is everybody divided, so each of the coefficients divided by 5 to the square root of 2. Now I can plug in y. I said x here, but I should plug in y. And I get 0, 0, 5 to the square root times 5 minus 3 here divided by the 5 to the square root of 2 because I normalized it as well. Gives me 22 divided by 5 to the square root of 2, which gives me B as the answer. Any questions? Okay, quick engagement questions. Jeremy. You all know the answers to the engagement questions if you want to go ahead and answer. So again, if you're going to use a plane equation to compute distance, you have to make sure that the normal used in the calculation is a unit normal. Otherwise, you divide. Notice I only divided by, I didn't divide by anything using the constant d. I only used a, b, and c to compute it because a, b, and c come from the norm, or from the normal. Okay, last call on the engagement question. And we'll do a quick why. Not too many, but enough to ask. Okay, last call. So going on to, moving on to chapter 9 now, which is 3D matrixy operations. So this one you should be able to do by yourself. You get 30 seconds. What is the transpose of the above matrix? Okay, last call. Okay, almost everyone got that one correct. For those of you who answered A, you might want to get tested for dyslexia. That's the anti-transpose. It flipped this way, not that way. You're having problems with left and right. That's the only way I know to get A. I have no idea how to get some of the other answers. They're just like perturbations or anything. The correct answer was D, transpose. Okay, pretty straightforward. Now let's do a harder one. You can talk with your neighbor on this one. What is the oops, sorry, I hit the question too quick. What is the determinant of A1, A2, and A3, right? So put those together into a matrix. And I just realized. Okay, I'll give you another 1 minute. That was the last question. So if you're using iRef, it looks like it's still showing you the old question. Make sure you're answering this question. The last question had the correct answer of D. That is not necessarily the right answer here. In fact, I'll give 4 people a hint. D is not the answer to this question. Most people seem to have gotten this, so are people still actively computing? Okay, I'll give you a little bit more. Okay. Good? Last call. So it was a bit of calculation, but most people got the correct answer, A. Okay, so again, this is a determinant, and you'll notice I actually am going to use the same process for determinants as I use for the cross product, and that's because there actually is a relationship between the cross products and the determinants. So I'm going to take the matrix, in this case, 1, 4, 7, 3, 2, 5, 6, whatever. Notice they were transposed, little t's here. Actually, it wouldn't matter if you didn't include the transpose because the determinant is the same whether you transpose it. But put those in. Then I'm going to do the first pass. I do 159 minus 168. Then the same for 267. Oops. Sorry. I was doing it with the other direction, but it actually still works out the same. So I can fix those and update the slide. But so the same crossing process works out. I can also do them on top of each other and cross them out that way. And that gives us an answer of 0. So sorry, I actually did this originally with the transpose, so I messed that part up. Okay. What of these below is the matrix that reflects around the vector? Sorry, reflects a vector around the plane x3 equals x1. So which of these is a reflection matrix that reflects around x3 equals x1? So for those of you who think you have an answer, because there's still some people computing, how do you check your answer? Yes, you can plug in some numbers and see what happens to them. So, okay, we'll give you another 20 seconds. Okay, last call. Oh, at the last second, some people switched over to the correct answer. The correct answer was B. Okay, not A. So what is A? If I had to describe A in words, what is A doing? So lots of people answered A. No, it's actually not a rotation matrix. So A is a reflection matrix, but it's reflecting around the plane x3 equals 0. Right? It's taking the positive x3 axis and making it the negative x3 axis. Right? But if I wanted to reflect around the x1 equals x3 axis, I'm swapping x1 and x3. That's what it means to reflect around that particular axis. So if I look at what is, then I just have to sort of say, well, I want to swap x1 and x3, right? And the matrix to do that moves, I want x1 to go to x3, so I make 0, 0, 1 for its vector. The middle vector doesn't change, and then the last vector I want to take x3 to x1, so I put it there. Right? So that gives us the answer of B. Right? Now this one is actually, another way of solving this one is, you'll notice that x2 had nothing to do with this question. So for some problems in 3D, you can reduce them to a 2D problem if you think of the right axis or the right plane to work in. So if I just worked in the x1, x3 plane, because x2 doesn't matter, then I can just view it as reflecting around a line that you've already seen before, which would be another way of solving that. Construct an orthogonal projection matrix that projects onto the line spanned by U. How many people have no idea how to solve this problem? See lots of puzzled people. Okay, so how would you solve this problem if U was two-dimensional? Okay, that did not help. Okay. We've actually solved this problem for the two-dimensional version once or twice before by creating an orthogonal projection matrix, right, using U, right? And the only difference now is it's in 3D instead of 2D. You really do a similar process. So this one, by the way, this was not in the chapter. If you're like, where was this in the chapter? This wasn't. Okay, this was a real test to see how much you can generalize. You'll see that lots of things we did in 3D were really the same thing we did in 2D, with just carrying around an extra dimension. So in 2D, we actually, so I'm just going to go ahead and we're going to ignore this question. I just wanted to sort of see how well people would do. So in 2D, we solved this projection matrix. We did this by building a projection matrix where I did U transpose, right? That's how I get a projection that will project everything onto the line. Well, it turns out I can do the same thing in any number of dimensions. I can take U transpose, which we call the outer product, and it will give me a matrix C. But I just wanted to sort of see how well people would do pushing beyond the limits of what you read to can you figure stuff out. Failed experiment. Okay. So let's consider the matrix A given here. What's its determinant? This is in the chapter. Okay, we got most of them here. We'll give it another 30 seconds. Okay, last call. Sorry. So most people got this. You're getting down determinants. The correct answer was B8. So, you know, there's the formula in the book for a 3 by 3, or if you use my approach, you just go cross, you get 4 minus 4, and then everything else turns out to be 0, but either way, you get 8. Okay, throwback from last week. Find the eigenvalues of A. Sure. Okay, we got most of the answers in. We'll give you another 30 seconds. Okay, last call. I guess some people have already ducked out. So most people got this. I think some of you actually exactly remembered. We've seen exactly this question last week, but we do the eigenvalues. We do the value minus lambda on the matrix diagonal. We compute the determinant, characteristic equation set equal to 0, and then solve for the zeros, which in this case are 3 and 1. Okay, so guaranteed your midterm will have a eigenvalue problem for 2D on it. So one last question, and then have a good day. Jeremy, can they be negative? They can, but in that case they weren't. Yeah. Well, he asked a generic question. I wasn't sure if he was saying, like, should they have been or could they have been? So if you start looking at program 3, just stick to part 1 where that will not change. You will project them onto the ground plane. That part will not change. The second part, part 2, we might make some changes to this week. But